Alright, we're back and now we're going to talk about the motor effect. We said earlier that a magnetic field is caused by moving charge and that a moving charge in a magnetic field will experience a force. That fact gives rise to the motor effect. If we imagine a magnetic north pole and a south pole near each other and there's a magnetic field in between them, so we can draw these field lines in, they would look something like that. Now let's imagine running a wire across this field. So we're going to put an electric wire here and we'll put some current flowing through this wire. So we'll call it I, that's the symbol for current. So imagine this current is flowing through this wire in this direction. Well, that's moving charge, and the moving charge as it goes through the magnetic field will experience a force. And it turns out we end up with a downward force all along this wire, because all that moving charge has a downward force. That direction is determined by the right-hand rule. If you put your fingers in the direction of the current flow, take your right hand, not your left hand, your right hand, and point your fingers in the direction of the current flow, which would be this way, the way this I vector is drawn down here, such that the fingers can naturally bend in the direction of the field, which is to the right in this diagram over here toward this south pole. Then your thumb will naturally point in the direction of the force, and that's those red arrows that I've drawn down, pointing downward. That wire will experience a force downward as a result of that charge moving across the magnetic field. Now let's take that same concept and apply it to a loop of wire. And the loop doesn't have to be round. To make it a little simpler, I'm going to draw it square. But first let's draw in these field lines. These would be the lines representing the magnetic field pointing from north to south. Now let's draw a loop of wire here. And I'm going to try to draw this in three-dimensional perspective. So it looks something like this. And we imagine putting electric current in one end here and it's coming out the other. So our current flow is around this loop. So the current is moving around the loop in this direction. And the thing to realize is that while the current's going down one side of this wire, it's moving across the magnetic field in one direction, and while it's moving down the other side of the wire, it's moving across the magnetic field in the opposite direction. So it will experience force in opposite directions each time. As the current moves in this direction, force is generated on this wire downward. And then as the current comes around and comes back down the wire on the other side in the opposite direction, force is generated on this wire upward. And you should see that that would tend to cause this loop of wire to twist. It would tend to cause it to rotate because you have an upward force on one side and a downward force on the other. And that produces a turning force, what we would call a torque. And that is the motor effect. A motor, as you know, is something you can plug in and turn on and it turns, like the motor for a fan, say a household fan for example. You plug it in and you hit the switch and it turns. You're sending electricity into it and the thing rotates. This is how it happens. This is fundamentally, now typically the design is more complicated than this, but this is the simplified version of an electric motor. You put current through here and it rotates. Now you ask, well, wouldn't the wire start to twist up? Well, yeah, it would, and there's little devices you can have to allow it to slide without the wires twisting. But don't worry about those details for the moment. Just understand why it works, where these forces come from fundamentally. They come from moving charges in the magnetic field. And every time the direction of the force is indicated by the right-hand rule. And that's the motor effect. If you want to see the right-hand rule in action here, you can imagine your right hand. So here are your fingers and your thumb. And your right hand, let's imagine the current flowing down this side of the wire. So your fingers are pointed in the direction of the current flow such that they can naturally bend into the direction of the field, the direction where those yellow lines are pointing. If you orient your hand that way, with the fingers pointing in the direction of the current such that they can naturally bend into the direction of the field, then your thumb naturally points in the direction of the force on that charge that's moving through the wire. And that's those upward arrows I've drawn there. And then the opposite would be the case over on the other side. We end up with a downward force. But that's the motor effect, and it's caused by forces that naturally occur when a charge moves across a magnetic field.